Okay, hello everyone. Today we are going to solve an important topic, electricity and magnetism, and the question is from Randall challenging problems and Gauss's law subtopic. So let's together first read the question to understand it, and then we can solve. So an infinity cylinder of radius r has a linear charge density. You're being given linear charge density, volume charge density, where r is less than r. We're being given rho at r is equal to r, rho naught divided by r. First question, draw a graph of for r versus x as it says there. Then we'll be given the charge within a small dv is dq. Integrate, use this fact to show that rho naught is equal to 3 lambda 2 pi r square r capital. Hint, let dv be the cylindrical shell of length L, radius r, and thickness dr. What the volume of such a shell? Then let's go to C. Use Gauss's law to find an expression for the electric field. Strength E inside the cylinder where r is less than or equal to r in terms of lambda and r capital. Does your expression have the expected value at the surface? R is equal to r. Explain. So this is our question. So now let's come to an important part of taking the important data from our question above. I hope the question is clear. We will put it aside and let's go to the solving the question directly. So from our question, first of all, we are going to take important. We have been given the first question. We need to draw a graph. First question, draw a graph of lambda versus x or r. That's the first thing I've been asked to do. So how are we going to draw a graph? In order to draw the graph, you need to know the relationship between rho and r. This relation comes from what you have been given from our question. Say rho is equal to r rho naught divided by r capital. It's from the question, whereby this is constant. So this shows that this is directly proportional to r. Okay? So to draw the graph, our graph will be as follows. A sample of a graph. The graph says that draw a graph of this rho versus x from x-axis that goes the cylinder perpendicular to the cylinder axis. Let's range from negative 2r to 2r. So the range from 2r to negative 2r. We can assume here is r negative. We can assume here is r positive. Here is the maximum rho. This is the rho column. This is the x-axis. So it means that as the r increase, also the volume charge density increase until it reaches a time whereby r is equal to r capital, as shows here. The same on this opposite side. So this is the sample of our graph. But beyond this r, which is 2r and above, and beyond this r, which is 2r and negative 2r and above, there is no volume charge density because charge is equal to 0, because this is outside our body, which is a cylinder. So B, we have been told that we need to prove that rho naught is equal to 3 lambda divided by 2 pi r square. We need to prove this. How can we prove this? By considering two things. First of all, linear charge density, which have been given from the question, linear charge density, whereby Q is equal to lambda L. First one. Also, volume charge density, we also have been given, whereby dQ is equal to dV, this one, rho dV. Okay? So let's integrate this, because we have been told if we integrate this charge total is equal to this one. So dQ is equal to rho dV. Upon integrating from 0 to V, from 0 to capital Q, we'll get Q capital is equal to rho dV, whereby Q capital, let's substitute this value. So lambda L is equal to rho dV. But there's a question hint. Let dV be a cylinder shell of length L, radius R, thickness dl. What is the volume of such a shell? So we need to assume we have been told to assume, let's assume this is a shell or a cylinder with an axis, okay, with radius R capital, with length L, but inside of this we can draw another cylinder like this, with a thickness like this, dr, with a small r. Okay? So what's the volume? In order to get the volume, dV is equal to circumference times thickness times length, whereby circumference of a cylinder is 2 pi r times dr times r. Okay? Then let's substitute here. So lambda L is equal to rho d 2 pi r dr. This and this will cancel. So lambda is equal to rho 2 pi r dr. Also, we need to know what this. We have also been given this is equal to r rho naught over r capital. So lambda is equal to r rho naught over r capital 2 pi r dr. Okay? So put the constant out, we'll have lambda is equal to 2 pi r capital, also it's constant, r squares will be inside dr rho naught. Okay, then let's integrate from 0 to r capital, because this is seen as radius r. Then what will happen? We'll come here to be lambda is equal to 2 pi rho naught divided by r capital. Upon integration, we'll get r cubed divided by 3 from 0 to r. So lambda is equal to 2 pi over r. Here it will be r cubed divided by 3. Okay, then lambda is equal to 2 over 3 pi naught divided by r square, and divided by r square. Okay, but we need to find the rho naught by making it as a subject. So it will be 3 lambda divided by 2 pi r square, which is the same as what you have been asked to prove. So let's now go to C. Let's go to C. C says that use Gauss's law to find an expression for an electric field whereby R is less than R capital. Okay? So, Gauss's law, if you remember, Gauss's law, area cosine of an angle is equal to Q in over epsilon naught, which can also be written as E area is equal to Q in divided by epsilon naught. And then, do we have another thing? No, we need to find the expression for electric field. From our formula, what is A? Area. Area of a cylinder. Before that, we need to assume we have been given a cylinder, a certain cylinder. Okay? A certain cylinder. Instead of which, let's draw a Gaussian surface. That's Gaussian surface as radius r, and length of it is small l. Okay? So area, it will be equal to 2 pi r l, small r, small l. What's Q in? This is the interesting part. Q in order to get Q in, let's revise back when integrating here. Okay, let's find the Q in. Q in is equal to rho dV as from here, and then we need to dV. We remember dV was the value of dV. Q in is equal to rho volume 2 pi r dr. It was 2 pi r dr times what? Small l. Now it's small l. That's the difference. And then what else is similar to this? We can check. Now, okay, let's do this. We have to remove this. So Q in is equal to rho. We have the rho here. R naught divided by R capital 2 pi R dr small l. But now we know the value of rho naught, which is equal to 3 lambda 2 pi R square capital. So Q in is equal to R over R 3 lambda 2 pi R square 2 pi R dr L small. And then 2 pi and 2 pi will cancel. What else do we have here? This will give, so Q in is equal to R square. We will have R square dr L over R cubed. Yeah? And
3 lambda.
Also we have 3 lambda. So this is on integration. So Q in is equal to, remove constants out, which is 3 lambda divided by R cubed is constant. What else is constant? Small l is constant. What else is constant? R dr. This will be on integration. After that, Q in is equal to 3 lambda L small divided by R cube. We are integrating from 0 to R because of this is our surface now. The results will be R cube divided by 3 to R, whereby Q in is equal to 3 lambda L divided by R cube. Here we will have R cube because it's 0 divided by 3. Okay? Then Q in is equal to, which one? 3 and 3 will cancel. So it will be lambda small l divided by R cube over R cube. Yeah? So, where is it? From our equation of Gauss's law, electric field area is equal to Q in divided by E epsilon naught. So electric field is equal to Q in over epsilon naught times area, whereby electric field Q in we have now is lambda L R cube divided by R cube. This is Q in divided by epsilon naught times area. Where was our area? 2 pi L, also small l. So this small l and this small l will cancel. Electric field will be equal to, do you have anything to cancel here?
R, small r.
We have lambda R cube
R square.
R square.
Small r will cancel.
Okay. This r and this one will be R square, which will cancel, divided by R cube epsilon naught times 2 pi. So electric field is equal to lambda R square divided by 2 pi epsilon naught R cube. So from our question, so that this one is an expression of Gauss of electric field by using Gauss's law in an infinity cylinder, infinity uniformly charged cylinder. Okay, so maybe clearly you can put it like this, as make it more readable. You can put it like this. Okay, the last one is D. That's your expression of the expected value at the surface. R is equal to R expected. So let's finish it. D, which is the last one. D. Last one, D. When R is equal to R, what does this mean? It means that this is on the surface, it's not inside of the cylinder. So that this expression that we got there, we say that electric field is equal to lambda divided by 2 pi epsilon naught r square divided by r cube. Now this expression, when we put r is equal to r, we will have the same expected value of the surface. Let's try. So lambda 2 pi epsilon naught. Here r square we put r capital divided by r cube. So E is equal to lambda 2 pi epsilon naught r. So this one, the formula that we got after finding the electric field on the surface of an infinity cylinder. So that this value is the same as the value of finding the electric field on the surface of a long uniformly charged wire. Yeah. So if we check this with the formula of finding the electric field of long uniformly charged wire, it's the same, whereby lambda is equal to 2 pi r. So this proves that finding the electric field on the long uniform charged wire is the same as electric field on the infinity uniformly charged cylinder. So that was all from the beginning up to the end. In case anything is not clear, you can ask. Don't hesitate to ask. How many?